Let's start with a problem that's surprisingly common in engineering,
Hmm.
even if maybe you don't think about it daily. Where do things usually break? Think about like a chain maybe or a bridge structure.
Mm-hmm. Usually at the joints, right? The
Yeah,
connectors.
exactly. It's often right there
Uh-huh.
at the connection points. But what if, and this is the really interesting idea, what if the strongest, most resilient materials weren't built with those rigid, those fused connections at all?
Okay, so built differently.
Built using something as simple and ancient as a knot, something you might do with a shoelace or maybe a climber uses, but shrunk down, way down to a microscopic scale. That's really the core idea we're diving into today, leveraging the kind of surprising power of knot topology for material science.
Mm.
We're looking at some really groundbreaking research into a new class of materials that, honestly, it defies conventional wisdom. Our mission here is to unpack how these tiny microscopic knots are creating materials that are just incredibly tough, super stretchy, and, could genuinely transform things. Everything from flexible electronics to maybe life-saving medical implants.
Yeah, this is really fascinating stuff. This deep dive is based on a great article. It's titled Knots Are Not for Naught: Design Properties and Topology of Hierarchical Intertwined Microarchitected Materials.
That's quite a title.
It is, yeah. It was published in a top journal, Science Advances, back in 2023. And the research team includes names like Widianto P. Mastopo, Sammy Shaker, Wei-Ding Deng, and Julia R. Greer. Their work really pushes the boundaries, of what we thought was possible with engineered materials. And they draw inspiration from some pretty unexpected places.
And for you listening in, what you'll discover is how a simple but actually quite profound shift in design thinking can unlock totally new levels of performance in materials. This isn't just theory, right? It's about seeing how these fundamental insights can lead to those real aha moments,
Mm-hmm.
about material science and its very real, tangible impact on the world around us.
Exactly. Think about your smartphone screen, maybe. How often does it crack?
Too often.
Right. Or imagine a medical implant that doesn't feel stiff but moves perfectly with your body. This research is getting right at those kinds of real problems.
Okay, so let's dig into that problem with connections a bit more.
Mm.
Traditionally, engineers design materials with these interconnected structural members. You can picture the beams in a lattice, maybe, or the framework of a building, even microscopic structures in advanced materials. These junctions where parts are, fused or joined together,
Mm.
they seem like they should be strong, right? That's the whole point.
That's the intuition, definitely. But what's truly fascinating here, and maybe a bit counterintuitive, is that while those connections provide a necessary framework, they're also a major, often overlooked, weakness. In many, let's say, conventionally engineered materials, these junctions act as stress concentrations.
Okay, what does that mean exactly? Stress concentrations.
Imagine it like a tiny pressure point where all the forces just kind of converge. It means that when the material is put under stress, pulled, bent, whatever damage, like tiny micro cracks, tends to start and grow precisely at these junctions.
Ah, okay.
And this ultimately limits their overall strength and, really importantly, how much they can deform or endure before they just fail, often catastrophically.
So the very thing we thought made them strong, the connection, is actually their Achilles heel. That is counterintuitive.
It really is.
But nature seems to have figured this out already, hasn't it? Natural structures, they seem to handle this differently. Can you give an example?
Absolutely. If we connect this to the bigger picture, you see many natural composites showing incredible toughness and strength by using these intricate hierarchical orderings. Think about bone, for example. Or even the structure of those deep-sea hexactinellid sponges. They look so delicate, but they're remarkably stable.
Right.
They're often designed to avoid these rigid, damaging junctions entirely. Instead, they rely on complex, interwoven patterns. It's almost like nature's been hinting at this all along,
Like a little design secret.
Exactly. Like, don't just glue it, maybe weave it or knot it. And this raises a really important question. How can we mimic nature's ingenious solutions and apply them in synthetic materials? How do we overcome these inherent weaknesses of our traditional designs?
Okay, this is where it gets really interesting. I mean, when you first came across this idea in the research, what was your reaction? Did it seem obvious in hindsight or just totally out there?
It definitely felt like a significant conceptual leap. I mean, for so long, engineering has focused on optimizing these fixed connections, making them stronger. This work really challenges that whole paradigm. It's truly pioneering, introducing a previously unexplored class of architected materials. And they're not just woven like a simple fabric, but specifically knotted at the micro scale.
Nodded. Okay.
And the inspiration isn't only from natural materials, though they certainly use similar principles. It's also from the ancient and frankly diverse world of knots themselves. Think about it tying your shoes, right? Simple overhand knot. Or the complex load-bearing knots climbers rely on.
Sure.
All the way down to the incredibly intricate tangles and folds of DNA and proteins within our own cells. The very topology of these knots, how the strands intertwine and lock together, allows for fundamentally unique mechanical behaviors, things that rigid connections just can't replicate.
So if they're ditching those rigid connections, what are the actual practical advantages? What do these micronauts give you in terms of performance compared to the old way?
Well, the core finding, the really big takeaway, is that this unique knot topology unlocks a completely new way for the material to deform. A new regime, you could say. When these knotted microstructures are stretched, something really unique happens. Instead of just stretching out until they break, like traditional materials might, the individual micronauts actually tighten.
They tighten.
Yes. This knot tightening mechanism is the absolute key to their performance. And it leads to some truly incredible improvements in their mechanical properties.
Wow.
It's completely counter to traditional material design where you expect things to stretch, thin out, and weaken. Here, the knot tightening means the material can get stronger and more resilient precisely when it's under the most stress. That's a real game changer.
That's a huge shift in thinking. Okay, give us some numbers. What kind of performance boosts are we actually talking about here? What do they measure?
The numbers are pretty staggering, actually. In the tensile experiments where they pulled the materials apart, these knotted structures showed roughly a 92% increase in absorbed energy compared to similar structures that were just woven without the knots.
92%. That's almost double the energy absorption.
Exactly. A massive leap in impact resistance. It means they can soak up far more force before any damage occurs, and it gets even more impressive. They also demonstrated an up to 107% increase in failure strain.
Okay, failure strain. That means how much it can stretch before breaking.
Precisely. So they can deform, stretch, and absorb far, far more impact energy and stress before they eventually break. They are incredibly resilient, incredibly tough.
And they manage this while being lightweight too, right? Because that's always the holy grail in material strong and light.
That's the key combination. Beyond the amazing extensibility and energy absorption, they also showed an up to 11% increase in specific energy density compared to traditional monolithic lattices of similar topology.
Specific energy density, so energy absorption per unit of weight.
Exactly. They're incredibly efficient at absorbing energy relative to their very low weight, so you get maximum performance without the bulk. This combination, high stretchiness, super low density, and the ability to sort of reconfigure their shape in a tunable way makes them uniquely powerful. It really opens up a vast array of potential uses.
Now, making these tiny, complex knotted structures, the team couldn't just use, like, standard manufacturing methods, I assume. They needed something special, right?
That's absolutely right. You can't just, tie microscopic knots by hand.
Yeah.
They fabricated these materials, specifically designs they called rhombus frames and octahedron unit cells at the microscale using a really precise method called two-photon lithography.
Rhombus frames, octahedron unit cells.
So like tiny diamond shapes and eight-sided cages.
Kind of, yeah. Think of them as these tiny, intricate, interwoven geometric shapes built from these polymer fibers. Two-photon lithography is basically an advanced form of 3D printing. It uses a focused laser beam to solidify a special light-sensitive liquid polymer, in this case one called IP-dip.
And it allowed them to create these incredibly complex, interwoven designs with really remarkable accuracy. We're talking individual fiber radii down to just 1.69 micrometers. That's unbelievably small.
Wow. Okay, you mentioned tunable properties earlier. What actually influences how these new knotted materials behave? Is it just the type of knot, or are there other factors involved that the researchers can tweak?
That's a really important question, and it shows the depth of their research. It's not just about the knot itself. They found that material properties, especially right at the surface of these tiny fibers, play a huge role. They didn't just demonstrate the knotting mechanism. They really dug into investigating how things like friction between the fibers as they rub past each other, different surface treatments, coatings, and even just the simple passage of time aging can significantly affect the mechanical performance. It's a complex interplay.
Like baking, you said.
Yeah, kind of. You think you have the perfect knot recipe, but then subtle things like surface chemistry or friction, like the humidity in the kitchen, change the outcome. These factors at the nanoscale have a profound impact.
That's a great analogy. So tell us more about those factors. What happened when they, say, coated these tiny structures?
Right, so for example, they coated some samples with a very thin, just 5 nanometer thick layer of alumina, that's aluminum oxide Al2O3, a process called passivation.
Okay, alumina. Pretty common material.
Very common. But what they saw was a significant drop in mechanical performance. The alumina coating made the structures much more brittle. They failed at much lower strains and loads, about 2 to 3 times lower than the uncoated, unpassivated frames.
Wow, so the coating really hurt performance.
It really did. It starkly highlights how surface properties, even a coating that's almost invisible, can either enhance or, in this case, completely diminish the unique advantages you get from the knotting mechanism.
So that tiny coating essentially wiped out the benefit of the knot. Okay. What about other treatments they looked at? You mentioned UV light.
Yes, they also explored the effect of UV irradiation. And what they found there was quite interesting, actually. Longer UV exposure, they tested up to 29 hours, generally strengthened both the simple woven frames and the knotted frames.
Strengthen them. How?
Well, it increased their load-bearing capacity. For instance, the 29-hour UV-irradiated knotted samples showed loads up to 90% higher at a given strain compared to the pristine untreated ones.
90% higher load. That's significant.
It is. The thinking is that the UV subtly alters the polymer's bulk and surface properties. Perhaps it increases the friction between the fibers.
Really? Okay.
And if you have more friction, that enhances the knot's ability to tighten effectively and absorb more energy before slipping.
That's fascinating. UV light as a way to tune the friction and boost performance. What about just, leaving them on a shelf? Does aging affect them?
Yeah, they looked at that too. Samples aged under normal lab conditions for over 75 days. And here they saw a clear difference between the two types of structures. The aged woven frames, the ones without knots, behaved pretty much the same as the new ones. Not much change,
Okay.
but the aged knotted frames were often significantly stronger. Over 40% stronger at a given strain compared to the fresh ones.
40% stronger just from sitting around. How does that work?
It's pretty intriguing. The hypothesis is that it might be due to environmentally induced changes in surface friction over time. Perhaps some surface oxidation or adsorption of molecules from the air increases friction, causing a kind of stick-and-slip mechanism as the knots tighten.
Huh.
It suggests that environmental factors, maybe even humidity or trace gases, could be another interesting way to tune these materials in the future, maybe even intentionally.
And does size matter at this tiny scale? Do these properties hold up if you make the structures bigger or smaller?
Good question. Their experiments showed that for the pristine, untreated samples, when they doubled the linear dimensions of the rhombus units from 70 micrometers across to 140, it didn't significantly change the normalized mechanical response.
Normalized meaning like strength per unit area.
Exactly. Strength or strain behavior relative to the size. This was important because it confirmed predictions from the analytical knot model they were using. It suggested the fundamental knot tightening behavior scales as expected within this range.
Okay.
However, the larger knotted frames did achieve even higher absolute failure strains, so they could stretch even further before breaking, which is definitely promising if you're thinking about scaling these up for larger applications. And what's also really fascinating here from a scientific standpoint is how well a theoretical model predicted all this. Specifically, an analytical knot model for overhand elastic knots developed by Jod and colleagues.
So a mathematical model could actually predict how these tiny complex physical structures would behave.
Pretty much, yeah. By fitting just one key parameter related to friction and the material's stiffness or modulus, this model gave really good predictions of the experimental results. And that's incredibly valuable. It gives researchers a powerful quantitative tool. It lets them understand and, crucially, optimize these complex, knotted architectures without having to run endless physical experiments. This theoretical underpinning is really vital for speeding up development.
Okay, so stepping back from the lab details, what does this all mean for you, the listener? This isn't just, cool science about micromaterials. It's about solving real-world challenges that could genuinely affect our daily lives. This research unlocks some incredible possibilities for materials that aren't just strong and light, but also super flexible, incredibly tough, and able to handle stress without just snapping.
That's absolutely right. The ability of these materials to handle large, repeated deformations, twisting, stretching impacts, without that catastrophic failure that is an absolute game changer across so many fields. Think about, say, flexible electronics. We all want devices that don't break easily. Traditional electronic components and the circuit boards or substrates they sit on can be very brittle.
Definitely. Drop your phone, the screen shatters.
Exactly. Now imagine a micro-knotted material used as the base for intricate electronic circuits. This would allow the whole device to bend, twist, maybe even stretch repeatedly without breaking connections or damaging components. This could lead to far more durable, far more adaptable devices, truly wearable tech that feels just like a piece of fabric, or maybe display screens that can fold and unfold thousands, millions of times without wearing out. It's a huge leap towards that next generation of portable, integrated electronics.
Okay, flexible electronics is a big one. What about the medical field? It sounded like there could be some profound implications there. Are we talking about truly new kinds of treatments or devices?
Absolutely. The potential in medicine is enormous. Consider something like hernia repair, for instance.
Okay.
The surgical meshes currently used for reinforcement are often made from relatively stiff polymers. Now, they work, but that stiffness can lead to discomfort for the patient because the mesh doesn't move naturally with the body's tissues. A knotted material with its built-in flexibility and toughness could provide reinforcement that's still incredibly strong, but much more pliable. It could conform better to the body's dynamic movements, withstand the constant stresses from internal organs.
So, potentially less pain, better recovery.
Potentially, yes. It could significantly reduce postoperative discomfort and maybe even improve the long-term outcomes for patients needing hernia repair or similar soft tissue support. Or, think even smaller scale, imagine tiny medical devices deployed directly in the bloodstream.
Wow. Okay, like nanobots.
Sort of, or maybe advanced stents, tiny
Yep.
sensors, drug delivery vehicles. These devices have to navigate incredibly complex dynamic environments inside the body. They face constant pulsatile forces from blood flow, bending as vessels move.
A really harsh environment.
Extremely harsh. Current materials might be prone to fatigue failure over time under that constant stress. But a micro-knotted material could be engineered to be incredibly resilient. It could absorb those repeated deformations potentially for years without degrading. This could make devices like next-generation stents, or maybe those tiny therapeutic medical robots, far more reliable and longer-lasting once they're inside the human body. The implications for less invasive, more effective, and longer-lasting treatments are just immense.
The implications really are huge. This research offers a path to creating materials that are lightweight, incredibly damage tolerant, and can be tuned, not just by their overall shape or the bulk material, but by how their tiny interwoven components interact, how much friction there is between them. It's a completely new way to think about designing materials, isn't it?
It truly is a new paradigm.
So we've journeyed from this fundamental problem, stress concentrations at junctions in traditional materials, to this elegant, almost ancient solution found in the art of knotting. And we've seen how that principle is now being applied with incredible precision at the microscale to create materials with just unparalleled toughness and stretchiness.
Yeah, this deep dive really highlights how digging into fundamental topology, how things are connected, and cleverly exploiting subtle interactions like friction at a microscopic level can lead to really extraordinary advancements in material science. It truly has profound implications for how we design things for a future where flexibility, resilience, adaptability, those are going to be absolutely paramount.
It's a great reminder, isn't it, that sometimes the most revolutionary innovations aren't about inventing something totally alien and new, but about looking at familiar concepts like a simple knot through a powerful new lens, like a microscope, and understanding the hidden power within. So as we wrap up, what stands out most to you from this deep dive? How might this whole concept of interwoven knot-based materials start to influence the next generation of products you use every day, or maybe even enable things you haven't even imagined yet?